Okay, so we're going to talk about the how to use computing cluster and basically the introduction the computing cluster. Um, First of all, what is a computing cluster? It is a group of interconnected computers that work together to perform the computationally intensive tasks. In a cluster, each computer is referred to as a node, and that is a really important concept to like keep in mind. The node, which comes from the graph theory, and it is like a cluster which it is like a graph, and each node is a computer and is a graph connected with with a group of computers, and that the graph is our cluster. Um, Basically, um, the organizational cluster you can see here there are terminal or clients, which is represent our terminal, and the login nodes, or they call it access nodes, which is the nodes we do most of the interaction with, and through the login nodes we can communicate and can ask the computing nodes to do their job. So it has it shows that the login nodes, access nodes, or sometimes called head nodes, usually just one or two, and a large like small number of access node, but we usually have a large number of computing nodes to do the computationally intensive job, and sometimes, for example, like for our fast cluster, we have thousands of nodes and have about 10 or 20 like logging nodes, and that's how the cluster is organized. And the jobs usually like run on the computing nodes by the scheduling program. Scheduling program is mostly has been used and nowadays become widely popular is a Slurm, which has been used in like more than half of the cluster I have been in contact with. And let's talk a little bit more about nodes. Each node contains about one or more processors, like CPUs, on which the computing takes place. Each processor has multiple cores. For example, the new nodes each contains two processors, and each processor has 16 cores. So each node, we have approximately like 32 cores in each node. That means like one of these nodes can perform 32 tasks simultaneously. A job that can be run on a single core. Assume the software is written to support parallel operation. A job may also run on multiple cores, on one or more cores, and even on multiple nodes at the same time. And that is done through the scheduling and distribution system. Then let's talk a little bit about the operating system and scheduling. The cluster run like mostly our Linux operating system. More specifically, the customized version of Red Hat Enterprise Linux are mostly dominated the market. And some clusters use a popular distro called Ubuntu. So Red Hat Enterprise is primarily dominant in the cluster market. And I see more and more cluster begin to use Ubuntu, but they all like different distros of Linux operating system. The environment that determines when your program will run is called Slurm, the scheduling system. Um, a computer on which you are going to run is actually a collection of computers called the what we call the cluster, and which is a whole bunch of computing node at this moment. Since there are more people who use the cluster than there are computers, the work needs to be scheduled. And of course, this is done by Slurm. So that is why in many cases, when you submit your job, you have to wait for a while until your job is executed by the scheduling system, because there are more jobs waiting to be run, and some people have high priorities, and some research group have paid for their resources, so they have a little bit higher priority in the scheduling system. Therefore, you have to wait for a longer time, and that's how some of your jobs may be like submitted to the cluster and waited for quite a few days before they like began to run. In order to keep track of who is running where and how and which node and core, we need a scheduler to allocate these resources. In job scripts, you define exactly how many cores you are required, as well as how many nodes if a job can span like multiple nodes. If resources are not available immediately, like Slurm will start reserving resources for you and launch a job when they are ready. And that's basically the brief introduction of operating system, of the scheduling system, and of the organization of cluster, and what are the nodes and access nodes and computing nodes. But basically, you only have to keep one thing in mind, that you should never run your job on the access node, or what we call login node. They are they're just for your interactions with the cluster, but they're not supposed to run your job, which is computationally expensive. You have to submit your job to the cluster through the following ways. And that's a few things I'm going to discuss with you, is how to run the job in cluster, and by following the scheduling rule. And the cluster, as we mentioned, is managed by the job control system and called Slurm. The tools you want to run are embedded in the command script, and the script is submitted to job control system using the appropriate Slurm command. And for a simple example, that prints the host names of a compute host to both standard out and standard error, create a file called host name slurm with the following content. And you can see that with the file containing those commands, and it will begin the print. And for example, we can see that the sbatch -n one, which means the number which designated the number of cores you requested, and the big N dash big N ensures that all cores on one machine, as usually that's the case, and sbatch T15, which is running time in minutes, and this job should be running for about 15 minutes, and after that it will be like terminated. And dash P is serial requeue, which means partition submit to that which partition or which nodes, which like partition of the cluster you want submitted to, and dash memory, which designated the memory you want to use. And here's 100 is memory per node you want to designate, you want to request, and that is 100 megabytes. And open node equals apprehend is apprehend when writing files, and dash O is the standard out goes to this particular file, and dash E, which is standard error that goes to this particular file, and then hostname, which is the command that has that executed. So that is basically very simple, like file preparing for your batch job, and that is a standard like Slurm syntax. When you submit this job, you basically write the following command into one file called hostname.slurm, and when you submit it, basically just by typing sbatch and hostname.slurm and then enter, return, then it's submitted. When command scripts are submitted, the Slurm looks at the resources you have requested and waits until an acceptable compute node is available on which to run it. Once the resources are available, it runs the script as a background process. return the output and error streams to the location designated by the script. And here shows how we monitor the progress. And your output and error files will be written to the directory the job starts in unless you specify the full path. So for example, if you always want your error file to write to your home directory, you should use sbatch-e and designated your home address, which is a system shortcut to your home directory instead of typing the full path. And that is usually a pretty neat way of designating the error file. So you can always check the error file to see how well is your job running. And here is another way to check the progress. Like you can monitor the progress of a job by using the SQ job -J with the job ID. And when you write that, when you submit that, it shows that how is your job running and what is priority and how much time it takes for running. And if it's still not running, then it shows the status of your job. Like for example, here, like you submit the host name .slurm, and you have the job ID like ends in 125, and you can check the status of this job by typing SQ-J and the job ID, and then you'll see that it is submitted to the partition serial queue, and the status ST shows like PD, which is not running, it's still waiting, and it has pretty it has priority like label, and it is waiting and haven't been running. And if it begins running, then the ST will shows as R, which is running. And that's how we check the status of the job we submitted. And there are always some cases when you submit a job in not a perfect way, and you discover there's some errors or bugs of your scripts, and you don't want to waste your time and computing resources. You have to like cancel it. So terminate a job just simply by typing s cancel and followed by job ID, and then the job you submitted will immediately be stopped. So that is a pretty frequent used function to terminate a job you submitted. And besides that, there are multiple cases we have to run an interactive job. Now, like batch jobs are great for long-lasting computationally intensive data processing. However, many activities like one-off scripts, and graphs, and visualizations, and exploratory analysis do not work well in a batch system, which is very common. But but also like resource intensive to be done on the logging nodes. As I mentioned, we never do any of the real computing things on logging nodes. Therefore, if you want to do something like interactive, and that is the way to go. The special partition on the cluster here, use an example, use the test partition for the interactive job. And that is designed for the responsive, interactive shell, and graphical tool usage. And you can start an interactive session using a specific flavor of the srun command. So srun-p designated the test partition, -p test, and then there's pty and memory requested 500 megabytes and requested times from 0 to 8 hours, and call bash. Like then you will be able to request about 8 hours of interactive session that you can run your resourceful computing there. srun is like sbatch, but it runs synchronously, and it does not return till your job is finished. So that's the difference. The example starts a job, like as mentioned, on the task partition with the pseudo terminal mode, which is pty, and an allocation of 500 megabytes of RAM for about, here is about 8 hours. like in this case, you will just get a shell pumped on the computing node. And now you can run any normal like Linux command, which is pretty neat way of running your job. Um, and uh, and when we are doing bioinformatics analysis, there are multiple cases, which is very common. You have to use the pre-installed software. As mentioned, like alignments, like RNA-seq analysis. Many of the softwares, you just need to like load them into the system so you can run them on the cluster. You don't have to reinstall them again. And that is how we load the software. The cluster usually like install the software in the form of modules, and we just check which modules, which software we want to use. They have already like installed most of the common software, especially bioinformatics analysis tools, already in the system. We just have to module load those software in the form of a module name, and after we load them, they're ready to go. They're ready to use. Very convenient, and this always coupled with when we submit some jobs that needs to require some bioinformatics tools in the command line form. We before we submit them in the files, we have one additional command that's load particular module. And after we load it, the next line, we can write the command that calling for the tools to execute it. So we can run those software directly, either in the in-tech session or in the batch job submission. And here is now how we request memory. Like you must declare how much memory you are using per job using like man or man per CPU contained command switches. By default, Slurm assume you will need 100 megabytes. If you don't request enough, like the job can be terminated. Sometimes I have to use big memory computing, and I have to request as much memory as possible. For example, sometimes over 256 gigabytes. And before I running that, I check the petition I'm submitting to. What are the maximum memory of that particular petition, and requested the biggest like memory I can for the large memory job I'm going to run. And here shows how we run how we request the memory for our job. And now let's come to some very standard usage example, and the three practices which I've been used a lot in my research. And as I prepared for my terminal here, let me share my terminal. You can see here, here is my terminal, and let's clear it. And the first job I'm going to submit, let's see, in here we don't have any other files, and the first job we are going to submit is the batch submission, but using a wrap command. Like here, here is the command I'm going to submit. So still like as batch -n, which means like one core, and the cores has to be on one node. And the memory I requested is about at the time I requested is pretty long. It's about 10,000 minutes, which is the maximum time I can get from this shared petition. And the petition I'm going to submit is shared, and the mail type for the notice is all, and requires about 6 gigabytes of memory. And the wrap, within the wrap is is a command line I'm going to execute it, which is the job. It's basically we put everything we want in the wrap field. And here I'm going to create a file in this particular folder, and the file name is called create task file. And that is how we submit it in a very simple wrap format. and we just hit return. Now it's submitted. It's submitted to this particular job ID. And now let's looking at what is the status of this job. So that S, Q, and job ID dash J, job ID. It takes a few seconds for a job to show up, so we just wait a little bit more time. And now let's looking at another way of submitting a job, which is here I prepared a testing file called download.slurm. And let's look at how is the download looks like. And we open it by vim download.slurm. And you can see here, there's pretty simple things and pretty like familiar. We call like 10 cores and the same nodes, and maximum time is about 10,000 hours. The partition we use is shared, and the mail type is none. We don't want any mail for this job. The memory requested about 1 gigabytes. And we first change our directory to this testing directory, and then we want to download is what we want to download is AG38 like FASTA file. That's pretty simple like execution. And let's see how it goes. So we submitted this job written in the download slurm, that is S batch download slurm, hit return. Now it is submitted to the job ID ended with 155. Now let's have a look what is going on with the previous job we submitted. That is ended in 153. Oh, you can see now this particular job is running, and sorry, it is waiting to be run, and that where the partition called PD. With the status called PD, so basically it's waiting to be executed. It's waiting to be run. And now let's look at the job we submitted for downloading. Let's download slurm. It's here. J, and ended 155. Now this job is not showing up because it takes a few seconds showing up. Now let's do another demo, which is request for interactive node. Now let's use the following command line for the running of interactive node. Like in this command line, like now is as run -n. We requested 1 core of the from the testing partition for about 8 hours using like 2 gigabytes of memory. And now we have been allocated of the resources. You can see with job ID 156, and now we're in the testing session. And we can do many like heavy duty job here as long as it within the memory limits, and we can use about 8 hours. And that is how we run the computationally intensive job. And now you can just use it exactly as your Linux machine. And it's very convenient, like neat way of running the job. And those command line of Slurm still used. For example, we want to see what is happening for the job that we submitted, or it finished running. And now, like the download Slurm is running. You see the partition, it shows it's running, and the status is R, is running, and it has been running for about 19 seconds. And that's the node that it has been running. Now let's see what is this particular job, like what is status. And we can see here the error, the output is 0, which means it there's no like particular error message. But we do create a file that we wish to create in the in this batch, in this submission job that designated. We want to create the task, the create task file .txt. Now this particular file is successfully created. So this job has quickly been executed and finished in the cluster, so it works. And now the downloading also works here. It is now downloading the particular file we requested. And the log of the downloading file can be observed here in the Slurm where the job ID out. So now you can see here that that is the log ID of how the downloading works. It is downloading at the current moment, should be finished pretty soon. So basically, that is all for the simple introduction. And yeah, let me know if you have any questions.